Is it visible to you? So good morning, everyone. In our last class, we had just started the time frequency methods, and I have given you uh, some insight why we need to have these time frequency methods for the analysis of the signals, because we have seen that even if two signal components they are having similar frequency profile, they may be different in nature in the spatial domain. So under this condition, our Fourier transform and the conventional signal processing techniques they fail. So for this reason, these joint time frequency methods are important. Okay, over there I then talked about the short time Fourier transform, and I told you that these are this continuous wavelet transform, discrete wavelet transform, wavelet packet decomposition, Wigner-Wille distribution, then empirical mode decomposition, and Hilbert-Wong transform. They are some of the important joint time frequencies transform. But in the introductory class, we will mainly be restricting ourselves towards the continuous wavelet transform and the discrete wavelet transform. Okay. So and also, yeah, I think I have discussed this one also, right? Yeah, short time Fourier transform we have discussed in my last class. Then today we will be starting with this continuous wavelet transform and the discrete wavelet transform. Now, before coming into the continuous wavelet transform, it would be very difficult for you guys to have an understanding what is happening over here in the continuous wavelet transform. Though it is the first transform which was developed in the wavelet category, wavelet transform category. However, I would first try to make you understand what happens in discrete wavelet transform. Then I would come back to the continuous wavelet transform. Now, I'm not going into the mathematical stuffs at this moment. We'll be discussing this when we discuss the joint time frequency analysis in our regular normal lectures. Okay. Now, over here, if you see, suppose you are having a signal xt, okay, and it is having a frequency component of 0 to fm. Say, for example, I take this as fm as 200. Okay. Now, what it does is that in discrete wavelet transform, we divide the frequency component. I am telling we divide the frequency component into two. Okay, two equal halves. So the first half it is regarded as uh, approximate coefficient, and it is nothing but the lower half of the frequency component. If you divide this 200 by 2, so we get 100. So in level 1 of decomposition, what we do is that we divide the frequency component into two categories. One is 0 to 100 and the other is 100 to 200. Okay, you got my point? So 0 to 100, the lower frequency band, it is regarded as approximate coefficient, and the higher frequency band, it is called as detailed coefficient. Okay. Now, in the next level of decomposition using the DWT, sorry, DWT, in the second level of decomposition, what we do, we had this A. So, again, we are having the frequency component as 0 to 100. So, we break it into two again. So, this one would be 0 to 50, and the second one, why initially a is coming, this a it is coming over here because it is the approximation coefficient from the level 1, and then the second one is the detail coefficient, so ad, and the first one is aa. Okay, so in the detail coefficient of the level 2 we would be having the signal component in the frequency range, okay, of 50 to 100. Okay, in the third level of decomposition, what you will be having, again this approximate coefficient from the level 2, it would be broken down and it would appear as AAA. Over here, what would be the frequency component? 0 to 25, and on the in the detail coefficient stuff, you will be having frequency component of 25 to 50. So again you can go for level 4, level 5, level 6 decomposition. Okay, now what are the things what you can get? So these terminal values, these these are called as discrete wavelet coefficients, discrete wavelet transform coefficients. Now over here on the right hand side, you will see that the first one, the A component, it is the sample ECG signal, and BTD is its DWT coefficients after second level of decomposition. Now if you look into the second level of decomposition over here, so we'll be having these coefficients. Are you getting my point? So first one is the D, that is this detailed coefficient. So this is the stuff. Then AD, this one is the AD, this one is the detailed coefficient, and last one it is the A approximate coefficient. So these coefficients you will get. If it is a level 3 decomposition, in the level 3 decomposition, the coefficients that you will be getting are these things. Okay, the area or the coefficients marked in black. Okay, so the main idea over here is that we are breaking down the signal coefficients based on the frequency. Okay, so if I say that I have broken the signal component, I have said signal component which is 20-second long, and it is having frequency component 0 to 200. Now say I have broken down the signal such that the two signal components, they will be having frequency components of 0 to 100 and 100 to 200. So what would be the signal length of the two coefficients that I have got? क्या होगा? What would be the length of the signal components or the discrete wavelet transform coefficients in the time domain? I have broken down the frequency component. So what should be the length of the signal or the coefficient? सेम होगा किसका? ओरिजिनल सिग्नल के हिसाब से सेम होगा. आर यू श्योर? हाँ हाँ, थोड़ा जोर से बोलो. तो थोड़ा जोर से बोलो. बट इट विल कंटिन्यू, मतलब कंटिन्यू मतलब व्हाट डू यू मीन बाय कंटिन्यूअस पैटर्न? What do you mean by continuous pattern? You had an original signal, you have broken down into two signals. So these are the coefficients. Okay. Now what is the length of this coefficient and what is the length of this coefficient? Half. कितने लोग बोल रहे हैं half? कितने लोग बोल रहे हैं ये same? So you are definitely correct. Continuous का आप क्या बोले? I couldn't understand. But the thing is that the coefficient I told you, the signal is being divided based on the frequency component. Okay. So हमारा जो time axis है, if you see over here, um, the first one was having 350 ये, okay. The second one should also have 350. Third one also will be having 350. All the signal components over here, it would be, should be here, okay. However, if you look over here, you'd say sir यहाँ पे तो आपका signal component these are decreasing. Now why this is happening? This is happening because in discrete wavelet transform there are two types of transforms. One is undecimated, which is basically the decimation means, I hope everyone knows the decimation. The word decimation. Decimation. Decimate मतलब क्या है? क्या हुआ? मुझे देख के फिर उधर देख रहे हो? हाँ बताओ, आप ही बताओ. What is decimation मतलब क्या है? Decimate कर देना. What is decimation? Decimation means breaking down. Okay. I will decimate you. So I will break you down basically. Okay. So decimation, there are two kinds of discrete wavelet transform. The first one is undecimated, which is the original one where we do not take out any signal component. However, in this case, when you go for the higher level of decomposition, and if you are having a large number of a large time domain signal, and if you are analyzing that, you will be getting a lot of coefficients, and it becomes very difficult for you to uh, store the data and analyze the data, because your size of the data will be too high. Because suppose first signal, original signal, it is say for example 1 kb data. Now if it is an undecimated one, so suppose after level 3 yeah, decomposition, you'll be getting 1 2 3 4 coefficients. So 4 coefficient का 4 kb plus 1 kb आपका original signal का, right? So you will be having total of 4 kb of coefficients and 1 kb of original data, right? Now if you want to do the analysis, you are not dealing with only one sample, you are dealing with hundreds and thousands of samples. So under that condition, you will be needing a lot of memory to store this data. So this is one of the negative point of the undecimated uh, this discrete wavelet transform. In that case, there is another transform which is called decimated wavelet, discrete wavelet transform. Over there, what happens? Suppose you are having sample number 0, 1, 2, 3, 4, 5. So in this level, after you have done this up to say 100, 350 samples, so every, so over here also in the A also you will be getting 350 samples. In the D also you will be getting 350 samples. However, when you are doing this, you will eliminate all the odd samples or the even samples depending upon you, and the new time domain which you will be having, it would be again time domain signal 0 1 2 ऐसा करके आपका 350/2 आपका हो गया, that's 175 180 something like this. You'll be getting the signal components. Okay. 150 और 25, हाँ 175 signals in both the stuffs. Okay, 0 to 175. Okay, for A and D. Now if you combine these two, your total sample length will be again 350. Okay, again if you, so here you will be having 0 to 175 sample length. Again if you break this down, again 175/2 उसका ये करके मान लो इसको 174 if you take it for the easier perspective. So we have it, so we'll be having samples 0 to ये 75, 87 points, 0 to 87. Again if you combine these two, you will be getting this thing. Now if you combine this 3 components, again you will be getting 350 samples. So what we want to create, we want to create coefficients in the in the decimated discrete wavelet transform, where the total length of all the coefficients would be equal to the same number of samples as in the original signal. So herein what is happening is that when you are storing the coefficient, it is again only 1 kb as compared to the undecimated one, where your with each level of decomposition, your coefficient what you call memory size, it will increase. Okay, so this is the thing. Now when we come to the, if you look over here, at every level we are dividing the frequency levels. Okay, now if you see, in this case the frequency level is quite small, the bandwidth is small. Okay, right, and at a higher level the bandwidth is higher. Are you getting my point? Bandwidth means what is the frequency range. So here, in other terms, if we look at it into the filter perspective, the width of the filter is smaller at higher level and width of the filter is bigger at a lower level. So here we are changing the width. That means now when we are changing the width, the changing of that width is regarded as scale. So what is, and here it is regarded as A. So at higher level your scale is low, at lower level your scale is higher. Now if you are having a filter whose scale is smaller, then it is good for the analysis of the high frequency signals. Okay, if this width increases, that means scale increases. Why this is so? Say for example, this is the smaller one. Now I analyze a high frequency signal over here like this, right? So it is able to accommodate at least one cycle of the high frequency component. Okay, हमारा Fourier transform में what was our knowledge, that when we are trying to do the Fourier transform, we should take the Fourier transform of at least one time period of the signal, right? उसका अगर कम लेंगे, we will not be able to analyze the signal. The same thing happens over here also. When your scale is smaller, low frequency component will not come within that small scale. Okay, however higher frequency component, they will fit in into the smaller scale, these wavelets, right? So we will be able to analyze the high frequency components. On the contrary, if we increase the scale, then it would become suitable for the analysis of the low frequency component also. Okay, say for example, there is a this low frequency component. Now if you see this red mark, it is, these are the high frequency component signal components. So they can easily fit into the smaller width, but the low frequency components, they are not fitting. So one cycle is not there, so we cannot analyze it. Okay, so this is how, while we change this scaling factor, we are able to analyze both the low frequency and the high frequency components. Okay, another thing over here in wavelet transform is, apart from scaling, I hope you have understood what is scaling. Now another part is translation. Now what is happening when you have scaled, you are scaling it in the time domain. Okay, so you have a signal component like this. So initially you used a small scale, this thing, you took the signal, did the A, then you have to translate this filter component. Okay, now this filter component, then it is translated, means it is moved to the next level, from here to here, then from here to the next level, then again from next level to next level. So in this way it will go. So at a particular scale, it we need to move this filter from 0 to infinity. Then again we have to increase the scale and again do the translation and do the yeah, repeat this procedure. So what we are doing over here, so what are these filters? These filters, they are called wavelets, which are present in the time domain. And what we are doing basically over here, we are basically convoluting these wavelets with the scaled wavelets with the signal components occurring at a particular time. किसी को कुछ ये? So here is a filter. Say for example, this is a wavelet. Okay, you have a signal. Let me draw it in another year. Okay, तो यहाँ पे क्या है? This is having a fixed scale, say A0. तो आपने क्या किया? ये वाला स्केल में यहाँ पे ये किया, you did the analysis. Analysis क्या है? We basically find out the correlation. Okay, correlation आपको पता है, if there is a match between two data points or a series of data points, then the correlation factor will be high, or if there is a mismatch, it would be 0. So it varies from 0 to 1 usually. Okay, आपने इस वाला पॉइंट का किया. Now then you move this point to the next level. Okay, again you do it, you will be getting a correlation point. You have done it. So this movement, when you are moving this filter, it is called translation. Okay, it is called translation. Okay, ऐसा करके अब you will go from 0 to infinity. Time, you will start from time 0, it will go to infinity. So this is the smallest scaled wavelet you have taken. Now next what you do, you increase the scaling factor. Time, frequency. Okay, so in frequency we also have the scale which is inverse to itself. However, if you remember, I discussed that when we are talking about scales, we do the scaling in the time domain. So say for example, if you have the longest scale, that means it covers all the time signals, it would go from 0 to infinity. Okay, now the thing is that when we talk about this discrete wavelet transform, we are basically talking about these digital signals, and we implement all the things in the digital domain. So we can eliminate this t with n. Okay, so if you see, when we are having the what do you call, the scale which is covering all the time, so we are towards the this low frequency band. Okay, now when we say increase lower this band, so suppose we have a signal up to, say for example, this n infinite over here. Okay, let us assume that our signal is up to that point. Now what should happen, we are reducing the scale When we are reducing the scale, then again we have certain band associated with that. Okay. Now when we have reduced the scale, our frequency band, this should increase. Okay. In the time domain, again, if we reduce the band like this, because all of this, when I am uh, scaling the band, that means in the time domain, whatever is the distance over here in the first half, the second half also will be having the same distance. Okay. Similarly, when we again go to the next level of scaling, now we are having four bands. Herein, the frequency band will again increase like this, and these bands, they would be again of equal stuffs. Okay. So when we talk about scaling, when we are changing the value of a, that means we are designing the filter in the time domain. However, since we are varying the width in the time domain, it also has replications in the frequency domain. Okay. 100, 100 to 200, 0 to 100, 0 to 50, to 200, then again 0 to 25, 25 to 50. Okay. 50 to 100. So हम अगर फ्रीक्वेंसी में इसमें ले लेते हैं तो इट बिकम्स इजियर. या टाइम फ्रीक्वेंसी का हम इसको तोड़ रहे हैं तो 200, 100. नेक्स्ट लेवल में क्या है 50. ओके. वो एक पर्टिकुलर लेवल तक जाएगा. अगेन इसमें क्या होगा, ये जो रहेगा यहाँ पे आपका दिस इज टाइम, यहाँ पे आपका एम्पलीट्यूड फैक्टर्स यू विल गेट. सो दिस इज 0 to 100. सो व्हाट इज हैपनिंग, 0 to 100, फिर 0 to 50, 0 to 25. So you will get a matrix something like this. Okay. So हर एक इसमें जो whatever you are getting, if you see the frequency components are getting compressed when we are going for the um, wavelet. Wavelet is basically, it comes from the uh, two words wave and let. So wave is any kind of signal plus let. Okay. So these wavelet, they are short duration signals. Okay. They are short duration signals and they have a average value of 0. Okay. Now this is about this discrete wavelet transform. So we have seen scaling. We start from a smaller scale. Smaller scale means high frequency. High frequency से suppose we have a wavelet of this one. So this will be accommodating, as I told you, high frequency. Now if I scale it up to double, it will be able to analyze frequency components which are lower, of lower frequency. Okay. Now since we are changing the scales, this type of matrix, this three-dimensional matrix what we get, say uh, frequency, time, and the color is the amplitude. So color matrix what we get, that is regarded as kilogram. Okay. Now in DWT you will find, since at every level we are doing this scaling by a factor of 2. Okay, by a factor of 2. So this will be more discretized in nature. In the continuous wavelet transform, we can use a wavelet which is having a width which is infinitesimally small. Okay, which is having frequency infinitesimally small. Okay. Now if you see over here, the high frequency component, if you see, the resolution is very high here, right? The resolution, it is very high. Now if you go for the next one, then what will happen to the next step? Suppose if you take it as a band 40 to 45, if you see over here, the resolution of the signal is very high. Now for the same area, if you see, this frequency component was here. Now in the same area, if you see in the lower frequency component, see, it has spread. Okay. So but however, in this case, if you see the image or the scaleogram what we are getting, it looks like an uniform colored image, because over here we can change the scale from, say, nearly equal to 0 to infinity. Okay, to infinity, right? Under this condition, what is happening, we can change this width of the wavelets by, say, some value which is tending to 0, which is tending to 0. I mean to say, scale, say, if you say that the width of the scale is x, so what I mean to say is that we can change this width of this thing to x plus delta x, where delta x, it would be tending to 0. Okay, and the other part will be quite infinitely wrong. So over here, if you see, in the 0 to 10 frequency band, if you find over, if you look it over here, we are losing the time resolution. However, if you go towards the higher frequency component, we are able to see the signal component in a confined zone. यहाँ पे देखो काफी एक broad सा you are getting the information. However, in the high frequency zone, you are able to confine the thing. So when you are increasing the scale, that means your frequency resolution is decreasing. If your frequency resolution is decreasing, your, what is happening, if your frequency resolution, if it is getting the whole, it is taking all that, yeah, if it is frequency resolution is decreasing, your time resolution will increase, and vice versa. Okay. So in the DWT also, if you see, as suppose if you are going towards the this again, if you plot it like this, say frequency again time, so here initially we will be getting a band where there would be A. Then we'll be getting another band like this one. Then this one. In this way, we will be getting the A band. Okay. So this band will also increase. It will differ, and this will be discussing these patterns um, at a later year. So this is called scaleogram. Now if you see the difference over here and here, it is looking as a very smooth picture. However, in discrete wavelet transform, whatever you will be getting, you will be finding that they are the images, they are quite, the scalograms, they are quite discretized in nature. Okay. So this is the difference between CWT and DWT. So in the DWT, if you see the detail coefficients, they are not again been broken down. So but there might be some information which may be hidden in these coefficients also, and we may want to increase the resolution over here, the frequency resolution over here also. So for that there is another uh, transform which is called wavelet packet decomposition, and this wavelet packet decomposition, like the breaking down of the approximate coefficient, the detailed coefficients, they are also broken. So we get dA dd over here. Okay. Now again, if you break down this dA, you will be getting daa and then dad. And similarly, this can also be broken down in the next level. So we will get dda and ddd. So that becomes the wavelet coefficient when both the approximate and the detailed coefficients, they are also getting uh, what you call broken down in terms of the frequency components. So now coming to the EEG application, so electroencephalogram. So there is a standard montage system where which is regarded as a 10-20 montage system. So over here we record the EEG signal by placing the electrodes at these marked positions. So FP means frontal. Frontal means in our forehead we place these electrodes. Then after a certain distance, then we have F, frontal part of the brain, F7, F3. Then FZ is the central part of the frontal lobe. Then F4, F8. Then T3, C3. At the different parts of the skull, we place the electrode, and from there we can take the reading. So when you take the reading, how the amplitude is varying, that we can check by measuring with respect to time. So this is the time. So you can say with respect to time, if you are giving some stimulus or something like that, so how the brain activity they are changing, you will get this kind of pictures. Say over here we have used a specific stimuli of light at 3 hertz. Now as the time is progressing, so if you see what is happening, the brain activity is changing. So you will, this is called brain mapping. Okay. So where you are looking into the amplitude based activity of the brain. Okay. So what are these things? These are basically the amplitudes. Okay. So this is called brain mapping, and you can record the brain mapping with respect to the time. Okay. So when you give a stimulus, this brain mapping, it helps you to understand which part of the brain it has been activated the most. Okay. Then we have visually evoked potential. In the visually evoked potential, what happens, we give this stimuli in terms of the frequency of light. So you have an LED, so you blink the LED at different frequencies. Say for example, over here we have given the stimulant at 3 hertz, 5 hertz, 10 hertz, 15 hertz, 20 hertz, 25 hertz and 30 hertz. And then with respect to time, we wanted to see how the brain activity is changing over a period of time. So this is called visually evoked potential. Why visually evoked? We are having light in front of us, which is activating our visual system through the retina. The light is entering through our eyes, it is falling on the retina, and it is activating the brain. Okay, um, uh, occipital part of the brain. Now, since it is activating the brain through the visual pathway, it is called visually evoked potential. Okay, then we can also have brain auditory evoked potential, uh, which is called BIEP, or brain evoked response auditory beta. So over here, instead of giving the information as information or the stimulus through the light, we use headphones to generate different frequency sounds, and then we measure the brain activity. Okay, so that helps us in understanding how the auditory pathway, that is from cochlea to brainstem, it is working, and those signal can be picked up through the EEG electrodes. So acquiring the EEG signal, so uh, first one, if you want to understand the brain activities at different regions, you can do it. As I told you, you can give uh, a stimulus and you can record the signal. And if you don't want if you want to have the control signal without that stimulus, you record the signal, and then before and after the stimulus you record the signal. The second thing is the understanding the changes in the visually evoked potential. So over here there might be some changes. This is a checkerboard, or you can have uh, this thing also, this LED panel, where the light will be generated at different frequencies. So without the stimulus you can find out, and with the stimulus also you can find out. Similarly, we can go for this beta. If you see, there are these headphones, and signal is being generated, or the stimulus is being given to the volunteer or the patient through this auditory pathway, and hence the name beta, brain auditory evoked potential. So this is an example, so where we give a coffee as the stimulus, so before and after the drinking of the coffee, and then the second stimulus was the visually evoked potential. When we gave the potential, how the signals were varying, that were recorded. Okay, so with this we can see that this analysis of the biomedical signal processing, it has got applications in a majority of the area. Okay. So whether you talk about the EOG, we have shown you EOG can be used for controlling signal components on these rehabilitative devices in a differential manner. Similarly, EMG can be used. Okay, then EMG can also be used to make video games for the differently abled person. Why this is so? This is so because uh, when you put the persons in under the rehabilitation program, if you are if they are trying to activate their muscle by normal exercise, it will be boring for them. However, if you can link that to some video game, that will have an psychological effect that they would like to win the game at every moment. Okay, so you have to give some reward to the patient so that they get motivated to get the thing. There is a recent thing in some of the life insurance stuff. So what they are doing, if you are having some smartwatch, this scheme has come newly. What they are doing is that if you are having a smartwatch which can record your body activity, and if you are going to a gym and doing the activity, they will record the activity, and based upon the how much activity you are doing, they will reduce your health insurance premium. Okay, so suppose if your health insurance premium in a year, I am giving just an example, if it is say 10,000 rupees, so if you work daily for say 1 hour, they may reduce the premium by 100 rupees or 200 rupees. So these kind of things are coming. So why these are coming? These are coming because you want to motivate the person so that they regularly do the exercise. Okay, and Here, what is the motivation? Motivation is that my premium will get reduced. And in the case of rehabilitation, if you disabled persons or the differently abled persons, uh, most of them they are quite depressed. So if you have to motivate, you have to give them some kind of motivation so that they can work. So what would be the motivation? The motivation would be using whatever the muscle activity you want to improve. Say for a paraplegic patients, uh, they are, or a what you call quadriplegic patient, you want to increase the movement of the hands. So you ask them to increase the activity of the hand, so that, say for example, we can go for this uh, throwing a ball into the basket. Okay, so ball may be onto the ground in the animation form. Then the more the muscular activity they do, the ball will go up, 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 and then it will fall through a hole from there. And that, the more he does that, the more points he will get. So that would be the motivation, and that can uh, help the biomedical engineer to design suitable programs, so that suitable customized programs for their patients. Okay, so you can do that. Then again, we talked about ECG. Is using the ECG signals, we can find out how the autonomic nervous system can be analyzed. Okay, then we can go for the EEG. EEG, we have seen, we can try to understand, by analyzing the EEG we can try to understand whether the visual pathway is okay or not, whether the what you call auditory pathway it is okay or not. Okay, so in this way we can do a lot of stuff by analyzing the biomedical signals. If you have any questions, we can discuss.